So I'm going to start off with molarity. So I'm going to move molality out of the way, and I'm going to bring in my first molarity problem. Okay, so this is one from the textbook. I decided to take one from the textbook, and it's a molarity problem. The question is, if 15.55 grams of sodium hydroxide are dissolved in enough water to make 500 milliliters solution, what is the molarity of the solution? Okay, so we're finding molarity, capital M. We give it the capital M because it's more important, it's used more frequently. Let me make a little note over here. See how this says ml like that? Well, you can write milliliters like that, and you can write it like that. I usually prefer this way. That's the way you usually find it on graduated cylinders. I don't know if you can read that, but this is also an acceptable way. You can do it either way. So first of all, let's see, what do we have here? We've got to set up molarity, okay, capital M. So we're solving for that. We're solving for molarity. And it equals liters of solution. Well, we don't have liters of solution, but we have milliliters. Okay, that's on the bottom. We have milliliters. So how are we going to convert milliliters into liters, to put it right there? Okay? And how are we going to convert grams into moles? By the way, how do I know which one is which? Which one is the solute in this situation? I need to know which one's the solute. Well, remember, the solute is less of the solution, and the solvent is more of the solution. Also, well, water is the universal solvent, so I was going ahead and assuming that water would be the solvent. It probably is. But look at this situation. 15.55 grams of sodium hydroxide. Okay, that's just a few grams, and this is the chemical, sodium hydroxide. It's just a few grams of it. Okay, try to picture that. If you had 500 milliliters of water, well, 500 milliliters would be this much water. Turns out that would be about 500 grams of water too. So there's way more water, so that means that water is the solvent, like it normally is. That's the solvent. And so then, what is the sodium hydroxide? That must be my solutes. Okay, so now we know which one is which, but I need moles of solute because grams isn't very fair. I have to convert that into moles to put it right there. But before I do that, I'm going to get the liters of solution. That's the easier one. Remember, I've got 500 milliliters of water. Okay, actually, it's not 500 milliliters of just water. It's enough water to make a 500 milliliter solution. So it's 500 milliliters total, including the solute and the solvent. Notice here, it says solution. So we want the volume of the solution, not just the volume of the solvent. So I misspoke there. It's 500 milliliters of solution. So remember that 1,000 milliliters is 1 liter. So if you want to convert from milliliters to liters, this is 1 milliliter right there, and this is 1 liter. There's 1,000 of these inside this. Well, all I have to do is divide by 1,000. So if I write 500.0 ml, I'm going to write it my way, and if I multiply by the conversion factor, well, that's dividing by 1,000 ml and 1.0 liter. Okay, so 500 divided by 1,000, well, that's pretty easy. Okay, pretty easy to do. 500 divided by 1,000 equals 0.500. So 0.500, and I could keep another 0, I'll just leave it like that. And now we write it as liters. Now liters is always capitalized. I know that's funny, but I do prefer to write milliliters this way, and liters is always capitalized. So boom, I've got my denominator, 0.500 liters. So now all I need is my moles. I need to get this. Okay, I need to get my numerator, moles of my solute. Well, I've got 15.55 grams of NaOH, sodium hydroxide. Okay, again, this one, sodium hydroxide. And I've got to turn that into moles. Well, we've done this in stoichiometry. We've done this before. If I want to go from grams to moles, how do you get from grams to moles? We need the molar mass. But I don't have the molar mass anywhere here. Oh, so I'm going to have to calculate the molar mass right here. Okay, so let's see. what do we have in this chemical? Let's look. Sodium hydroxide. We've got NaOH. So we've got, let me circle them in red. We've got sodium, we've got oxygen, and we've got hydrogen. And there's really one sodium, one oxygen, one hydrogen, one of each. We're just adding them together. So if I put in the masses and add them together, 22.99 plus, well, this rounds, this is 1.008, but if I round that to the hundredths place, it's 1.01. 1.01 equals, okay, plus the oxygen. And oxygen, of course, rounds to 16. So I get this really nice molar mass. We get a really, really nice molar mass of 40.00 grams per mole. That's the molar mass of sodium hydroxide. A nice, nice round one, okay? So now let me wipe that off. We got that molar mass. Remember the 40. And, okay, and, whoops, and if I write that right here, okay, we've got 15.55 grams, so then the 40.00 grams of NaOH has to go on the bottom, and then 1 mole of NaOH has to go on the top, right? So it's really 15.55 divided by 40, isn't it? The grams of NaOH are going to cancel out, and what I will get as my answer here, the units will be moles of NaOH. Okay, barely fit that. And so let me just divide it. This one isn't easy to do in your head. 15.55 times 1, I'm going to skip that, divided by 40 equals 0.388. So I'm going to, and it's moles of sodium hydroxide. So I'm going to keep all those digits right now, and I'm going to put them right here, and maybe I'll round it when I get to my answer. And then, of course, that's moles, and it's NaOH. So now, if I want to solve this, I don't have room to write it over here. Let me just put a circle around this one, and then I'll put my answer down below here. I've still got this on my calculator, 0.388 moles of sodium hydroxide. Then I just divide by 0.5. I could put in the zeros if I want, that won't matter. And dividing by a half is like doubling. So what I get here is molarity equals 0.7776. And then what are the units? Well, the units are moles per liter. And then sometimes we identify the solute, and you could write NaOH. That's the normal way to do it. But you know what? We want to round this off. So I'm going to also write one more step. I'm going to round this better. We're going to round it to the hundredths place. So what would that round to in the hundredths place? Okay, it equals 0.78. And then I'm going to show you another trick, because molarity is so important in chemistry that they gave it its own unit, kind of like the joule got its own unit. Think about that. And like density didn't get its own unit. So there's a much easier way to write the unit. You can write it just capital M. So it's funny that the variable and the unit are the same. So now that this is getting messy, I'm going to rewrite my answer one more time to make it nice and neat. Molarity equals 0.78 M, and then I can identify the solute. I should write it over here as well, NaOH. So then this would be my answer. Okay? So what is the molarity? Make sure that I was looking for molarity. Make sure you know molarity is capital M. Okay? Molarity is the default that we use in chemistry. Most of the time, if we go into the chemistry storeroom, most of the chemicals are labeled with an M like that, a capital M. Be very careful to make your capital M's pointy. Make your capital M's look like that. Don't round them off. If you round them off, it looks like a lowercase letter. So even if you don't normally write M's just like this, please do it for the variable and for the unit. Okay, so we've solved for the molarity of this particular solution. Okay, next one. The next one is another molarity problem. Okay, this one is how many grams of HNO3 are required to prepare 2,500 milliliters of a 6.0 molar, that's the way we read that, solution. So this one's a little different because remember, molarity, which is capital M, molarity equals moles of solute over liters of solution, right? So here we're given the molarity and we're given the liters. So what do you think we're solving for? If we have these two, we're solving for moles. But wait a second, it's not asking for moles, it's asking for grams. So what we have to do in this situation is we have to solve for moles and then go backwards and turn it into grams. The chemical that we're dealing with here, HNO3, is called nitric acid. This is the one that reacted with the pennies, with the zinc and the copper, okay, pennies. We saw that reaction producing the brown pollutants, okay, the oxides of nitrogen. So let's just get started. If we've got molarity, well, we've got that. This right here is the molarity. So make sure to put that in the correct place. 6.0 molar, remember I could also put moles per liter, but this is the easier way to write it, equals, and then I need my numerator and my denominator. Actually, I'm solving for this, I'm solving for moles, so I'm just going to put an X right here. This is what I'm solving for, this X. So we don't have the liters of solution, but it says that it's this volume of solution, so all I have to do is turn that into liters. What did we do last time? Oh yeah, we divided by 1,000. You know what, there's an easier way to divide by 1,000. When you divide by 1,000, move the decimal 1, 2, 3 times. It winds up right there. And that's a much quicker way to convert from milliliters to liters. You're always going to divide by 1,000. You're always going to move the decimal 3 times. So let's just do that. So that would give me 2.500 liters. And that's what I need. It needs to be in liters. But now we have to solve for that X. We need to figure out what that is. Well, what's the best way to solve things? Remember, I'm a big fan of cross multiplication. So you might say, wait, how can I cross multiply this when there's nothing in the denominator on this side? But actually there is. There's always, if you want it, you can, let me just do it in blue. You can always throw something over 1, because if there's no denominator, the denominator is always 1. And then notice that these two numbers would be diagonal from each other. If I wrote it correctly, those would be diagonal. We'd multiply those, and then we'd divide by the odd one out, then we would divide by the 1. So we're going to multiply these guys together, that's the first step. Then we're going to divide by 1. Well, that doesn't change it, so it's really the multiplication that gets us to the number we need. So let's see. 6 times 2.500 equals, and what do you know? It equals 15. It equals 15.00. Oh, and what would my unit be here? This is getting confusing because I'm using those. Oh wait, what am I solving for? I'm solving for that. What units would that have? That X would be in moles. And then which chemical would we be talking about here, which is the solute? Well, again, that's a whole lot of water. That's very little of the nitric acid, HNO3. So we're talking about that as our solute. Remember, solute is less of a solution. Okay, now the only problem is I just solved for X. X equals this. That's the moles. But the problem is it's asking me for grams. So if I take my 15.00 moles of HNO3, how do you get from moles to grams? Do you remember that from stoichiometry? How do you get from moles to grams? The same way you get from grams to moles. Use the molar mass. So again, I'm busting out the periodic table. This time we're talking about this chemical, HNO3. So let's see, we've got hydrogen, we've got nitrogen, and we've got oxygen. So let me write them out. 1.01 gram per mole for the hydrogen, 14.01 gram per mole for the nitrogen. And oxygen is 16.00 grams per mole. But how many are there? It's HNO3. So I've got to multiply this times 3. So that gives me 48. So 48.00 grams per mole. Okay, so let's just add those up real quick. 1.01 plus 14.01 plus 48 equals, and you know, you could do it on paper, but just to make sure, just to be very careful, 63.02 grams per mole. So if that's the molar mass of nitric acid, well, then I need to put it right here. I need to put that molar mass in this equation. But we're starting with moles. So where is the moles going to go? We've got to divide by moles. It's a molar mass, so it's 1 mole. And then on top, what I'm going to need are the grams, and we just said 63.02 grams, and these are both HNO3. Okay, it's the molar mass of the chemical, but this time with grams on the top. And you know what? That will give me my final answer. So let me just wipe this off so that it starts to dry for the next one. So notice we always have to know how to calculate molar masses because that's used all the time in chemistry, all the time. Okay, so now, what do we have to do? Oh, it's 15.00, if I want to type those in, times 63.02, because it's 15 moles, each mole has that mass, equals, well, this should be a really big number, and it is, we get 945.3, and what would my unit be here? Well, you know what? The moles of HNO3 are going to cancel. I'm going to have grams of HNO3, of nitric acid, and then guess what? That should be my answer. That should be my answer right there. Should be my answer. Let's make sure that's what we were looking for. We were looking for grams of HNO3. This is grams of HNO3. Boom. Second problem is done. For the third problem, I'm going to do another molarity, but this one, after we use it for molarity, I'm going to use it again for molality. So we're going to use basically the same problem twice, just to show you the difference between molarity and molality. Okay, so again, this is a molarity one first. If you dissolve 50 grams of C12H22O11 in 100 grams of water, the volume of the mixture is 108 milliliters. What is the molarity of the solution? So we're getting, again, molarity with an R, molarity, capital M. So we're solving again for capital M equals. And what we've got to figure out here is which one of these two numbers are we going to use here? This is interesting. It's kind of a little more confusing to figure out what we're going to do here. But first of all, let's mention what this chemical is. C12H22O11 is sucrose. It's another carbohydrate or sugar. And wow, that's got a crazy molar mass. This is going to be a much harder one to calculate. So we're going to need to do that actually right near the beginning. But before we do that, let's see what we can put into our equation. Do we have the molarity? No, it's asking us for the molarity. That's our unknown. Do we have the volume? I think so. Let's see. This is the 100 grams of water. Do I use that to get to liters of solution? No, it's liters of solution. So by the way, which one is which? Which one is the solute and which one is the solvent? Well, clearly, there's only 50 grams of this and 100 grams of that. They're both given in grams. So most likely, that one is the solvent. Water, the universal solvent, is probably going to be your solvent. And so then this one would be my solute. Okay. So if I've got 50 grams of it, 50 grams 50 grams of, I'll just write sucrose, then how am I going to turn that into moles? How am I going to put it up there? That's tricky. Well, I need to get its molar mass. So we'll do that in a second. But again, which number do I need here to get my liters of solution? Well, it's 108 milliliters. The mixture, well, that's the whole solution. The mixture is both of them together. So remember the easy way to convert from milliliters to liters? We're dividing by 1,000, so 1, 2, 3. It goes before the 1 right there. So then what would my volume, what would my liters of solution be? Well, that's easy. 0.108 liters. So now if I can just put that in, then I can solve for my molarity. So here we go, sucrose. Let's do this one. We obviously need the molar mass of sucrose. So what chemicals does it have in it? Well, it's got all nonmetals. Carbon, oxygen, and remember, hydrogen way over here is a nonmetal. It's just the only nonmetal on this side of the periodic table. So why don't we just write the molar mass of each chemical, okay? We'll write them in the order they are in the formula. So carbon is 12.01 grams per mole. Hydrogen is 1.01 grams per mole. And oxygen is 16.00 grams per mole. But the problem is there's a lot of these. There are 12 carbons. There are 22 hydrogens. And there are 11 oxygens. So we have to multiply each of those to get the contributions. Well, I can see that that's about 12 squared. That's going to be close to 144. 12 times 12.01 equals, yep, 144.12. And that's, of course, grams per mole. That's the contribution of the carbon. Oh, and this one's easy. 22 times 1.01, it's going to be 22.22 grams per mole. Let's just double check that. 22 times 1.01 equals 22.22. And then for the oxygen, well, it's 11 times 16.00 equals 176.00 grams per mole. So this is still on my calculator. I'm going to start with that one, and then I'm going to add the one above it, 22.22. Then I'm going to add the one above that, 144.12. Boom. And I get the molar mass of sucrose, which is 342.34 grams per mole. That's a really big molar mass, because look, we're adding up all that stuff. So it's a nice big one. Okay, it's a nice big molar mass. So now remember, even though it's a little harder to calculate that molar mass, we use it in exactly the same way as we did before. Now, where do the grams need to go? Top or bottom? Well, I got to get rid of grams, so grams have to go down here. I'm just writing sucrose just to save time. I could write out the formula for sucrose. I could write out C12H22O11. And then on the top, it's going to be moles. Well, it's going to be 1 mole of sucrose. Okay, and then what did we get? Oh yeah, we had 342.34. So again, we're going to be using this a little more, I believe. So I'm going to wipe that all out. And then that will give us, then we can convert it into moles. So let's see. Oh, I can't use that. I have to clear it. So 50, which is what is given, grams of sucrose, times 1, well, I could do times 1. Still 50. And then divide by 342.34, just be careful to type it in correctly, equals, yeah, and of course, that's a little number divided by a big number, so it's going to be very tiny, 0.1461. You know what, I don't think I'm going to round that yet. I just round it when I get to my answer. I could round off that 1, I'll just keep it for now. Okay, and then of course, what cancels? Grams cancel. So then this would be moles that I'm left with. And this time I'll write the chemical formula C12H22O11 for sucrose. So where does that go? Moles of sucrose. Isn't that my solute? So doesn't that number go right there? Oh good, so the way I've written this, I've left space there. So let me just write it just like that. 1461 moles of C12H22O11. I'm not being lazy this time. And, all right, so these two numbers get divided. Oh, look, I've still got it on my calculator. So all I have to do is divide by the denominator. And notice that this number is smaller, so I'll get a number bigger than 1. So divided by 0.108 equals 1.35, and there's a 28 there, I'm just going to round those off. And then moles per liter, I could write moles per liter. What's another way to write it? Oh yeah, capital M, that's the unit. I could write moles per liter, that's fine. And then usually we indicate what the solute is. C12H22O11. And then that should be my answer. Let me put a nice circle around my answer. Oh, is that what I was supposed to get? It says, what is the molarity of the solution? Well, that is a molarity, isn't it? That's molarity, capital M, so we just did that.